So we are in 16th tutorial where we are going to discuss few problems based on the network theorems in the frequency domain. We have already covered these theorems during our lecture class, but in this tutorial we will see few more other problems and just a revision aspects. So the contents that are going to be covered in the frequency domain problems are basically the Ohm's law, KVL, KCL, that is Kirchhoff's voltage law and Kirchhoff's current law, voltage division, current division rules, mesh analysis together with super mesh analysis, and nodal analysis together with super nodal analysis, Thevenin's theorem and Norton's theorem, source transformation and maximum power transfer theorem. So these theorems are very important from the frequency domain aspects. We have already solved these problems in the DC circuits. Today in this tutorial we are going to see the problems based on frequency domain aspects. So first we'll see how to solve the fundamentals, voltage division and current division problem. So if you have a source current, then you have to determine the current I0. So let us see the first problem, how we are going to see. So in this problem, you can see that the current is basically a function of time. It means that the current is basically a AC current. So it is an AC current, alternating current, and we have inductor and capacitor in the circuit. So apart from resistor, we have inductor and capacitor. So obviously this problem lies for the AC circuit. Now how do we approach this type of problem? So that is very important to understand. The first thing that we are going to note down is the current is represented in the time domain, which is the instantaneous current. We have to convert the instantaneous current in the phasor form. So here the maximum magnitude of the current is 5, whereas the frequency is 10 and the angle of the current is 40 degree. So we can represent that current in the phasor form as the magnitude 5 with angle 40 degree. Now once we have got the current in phasor form, we can obtain the inductor and capacitors into their respective inductive reactance and capacitive reactance, because all the problems will be solved in the impedance form. So here, since the capacitor is given as 0.1 farad and the frequency is 10 radian per second, we can convert the capacitor into its equivalent capacitive reactance. So Xc is the capacitive reactance, which is equal to 1 by j omega c. Now here, since omega is equal to 10 radian per second and the capacitor value is 0.1 farad, we can obtain the equivalent capacitive reactance. So this unit will be in ohms. Similarly, the inductive reactance XL will be equal to omega L, where we can, and we have a J symbol here to include the direction of the current with respect to the voltage. Then we have the inductance in impedance format, that is the inductive reactance is J2. So we have got all the parameters converted into its equivalent impedances. Now we can see that these 4 ohm and the inductor are in parallel. So we can obtain the equivalent impedance Z1 for the resistor in parallel with the inductor. Now this, if we represent this one with Z1, then we have to convert that, or we have already obtained the equivalent reactance for that. So the Z1 that we are getting is 0.8 plus J 1.6. Similarly, we have 3 ohms which is in series with 0.1 farad capacitor, and we have already obtained the equivalent reactance of the capacitor, and then we can say that it to be Z2. So we have obtained Z1 and Z2. Now the circuit that we have got it is basically a current source, the impedance Z1, and there is another one impedance, that is Z2. So Z1 and Z2 are in parallel with the current source. We have to get what is the current which is flowing through Z2. Now we can apply the current division rule. So what does the current division rule says? That the current through a particular element is basically the source current Is, which is in phasor format, and the parallel of the impedance. So we have Z1, the parallel of Z2. So we can take that in the numerator, and in the denominator we have Z1 plus Z2. In this way we can calculate what is the current which is flowing through Z2 by simple one formula using the current division rule. So this current division rule says that the current which is obtained in the polar coordinate, we can represent the result with a magnitude and the angle, and then we can convert that current in the time domain. So here we have the maximum magnitude of the current is 2.325. So here we can say 2.325, and since the current source current is in the form of a cos, so we can say that this is also in the form of a cos the I naught. Frequency will remain same, that is 10t, plus the angle that we are getting for the solution of current I naught. So in this way we can represent the final answer in the time domain format, which is the instantaneous current. Next problem, you have to find the potential V naught. So here you have to find the potential V naught in the figure. So we have an inductor which is 0.1 Henry and a capacitor of 50 microfarad. If you can see, the source is a function of time with the frequency is equal to 200 radian per second. So we will be approaching this problem with the step that we have learned in the previous problem. So the capacitor and the inductor has to be converted into its equivalent capacitive reactance and inductive reactance so that we can get the unit is in ohms. So the equivalent ohms that we are getting is minus J100 and J20, the value of XL. So XL and XC we have obtained, and omega is equal to 200 from the problem. Now, once we have obtained this, we can reduce the circuit into simpler format, where we can have the parallel combination of 50 ohms which is in parallel with the capacitor. The capacitor value is minus of J100. So the equivalent impedance of the parallel combination, we can use it, that we can use at Z1 Z2 by Z1 plus Z2, where Z1 is the resistance 50 ohms and Z2 is basically the capacitor value. Now we have obtained the equivalent impedance, which is 40 minus J20. Now all these impedances, other impedances, if I take this one as Z3 and this one as Z4, so all the impedances are in series. So the equivalent impedance in series will be equal to Z equivalent 1, which we have calculated here. Then we can add up Z3 and Z4. So this will be the net equivalent impedance for the entire network. Now we can apply the voltage division rule. So our circuit is, we have a source. So the source, if I take Vs, then we have one impedance, that is the total impedance or the series combination of these two. Now one thing is that we need to calculate the voltage across this impedance. So if I take the Z4 into combination, then I will be not able to find the voltage in one step. So what I can do is that I will be taking the series combination of only these two impedances, and then that will be in series with Z4. So if I take the series combination of Z equivalent 1 plus Z3, then I will be having the Z4 intact, through which I need to find the voltage V0. So the voltage V0 we can find using the voltage division rule, where the voltage V0 is equal to the source voltage Vs multiplied with the impedance through which we want to get the voltage. So that will be equal to Z4 on the numerator, and on the denominator we will be having the total impedance of the network. So we have Z equivalent 1 plus Z3 plus Z4. So we will be getting the voltage as 17.14 angle 90 degree. Now we need to convert that in time domain form, that is the instantaneous, where the source voltage is in the form of a sine and the frequency is 200. So I can write that the maximum amplitude of the voltage that I got is 17.14. We have a sine component here, omega t plus 90 degree, which we have got the angle for the voltage. Now we can represent this result either in the form of a sine or in the form of a cos with appropriate taking into account the angle of the voltage. So we can represent in the form of a sine or in the form of a cos, anything, depending upon whether we can take full account of this phase angle. Next we'll take the mesh and nodal analysis, which will be dependent on KCL and KVL. So the first problem in mesh analysis is you have to determine the potential V naught. So potential V naught is across the 50 microfarad capacitor. Depending when the source voltage Vs1 and the source voltage Vs2 is given. So we have Vs1 and Vs2, the two source voltage, which are basically the function of time t. So both are function of time t. Now here we have the frequency as 100 and here also the frequency is 100. Since in AC problem the frequency has to be constant, so we need to check whether both the frequencies are same or not. If both the frequencies are not same, it will not be possible to solve the problem directly using the circuit theorem. Okay, so we have the inductor which are represented in millihenry and capacitor is in microfarad. So as usual we have to convert all the inductors and capacitors into its equivalent inductive reactance and capacitive reactance. So XL will be equal to J of omega L and XC will be equal to 1 by J of omega C, where omega is the frequency which is constant throughout the network, which we can obtain from the source voltage instantaneous equation. So we have converted all the inductors and the capacitors into its equivalent reactance. Now for the new circuit, we will be having three mesh problem. We have mesh 1, mesh 2 and mesh 3, which are the independent loops in the circuit. Now we can write the KVL equation. So KVL equation says that algebraic sum of the voltage in a closed loop is basically 0. Now these voltage can be represented in the form of Ohm's law. So in the Ohm's law we will be having the current multiplied with the impedance Z now. So here we are writing all the three equations, mesh 1, mesh 2 and mesh 3 equations depending upon the individual current. Now the unknown variables are the current I1, I2 and I3, which are flowing in the individual meshes, and we can substitute all the sources and all the reactances and the impedances of the network. So we have three equations in three variables which we need to solve. The three equations in three variables can be solved in the form of a matrix where we can write the constant term as A into X is equal to B. Now we have to find this X, which we can obtain as A inverse into B. So we have to obtain the inverse of this matrix, which is usually not possible in calculator because it is in complex domain. So 3 cross 3 matrix inverse we have to find out step by step using the Cramer's rule. So once we solve the values of I1, I2 and I3, we can determine the potential V0. So V0 is basically between the two loops, that is the second loop and the third loop, and the capacitor is 50 microfarad. So 50 microfarad is equivalent to minus of J 200. So we can write the expression relating the voltage, impedance of the capacitor and the current. So I2 and I3 are flowing in the reverse direction. So we have I2 minus I3 and the net reactance is minus of J 200. We can find the I1, I2, I3 from these equations, which we can substitute the value of I2 and I3 and then we can obtain the value of the potential V0. Now this is in the phasor domain, which we have to write it in the time domain. Then the maximum magnitude is 56.26. We have the source in the form of a cos and 33.93 is the angle and frequency is 100. So we can represent the voltage in the form of a time domain problem. So next problem, here we have to find the potential Vx. So Vx is the node voltage Now the sources V1 and V2 are given to us. Now see one thing, the source V1 is in the form of a cos, whereas source V2 is in the form of a sine. So appropriate sign convention should be there so that we can bring both in the same form. Next thing, the frequency omega for the two sources we have to note down, that is constant at 1000 radian per second. So we can solve this problem because the frequency is constant. We have one inductor that is 10 millihenry and one capacitor 0.1 millifarad. So here we have to convert this one in inductive reactance and this one as capacitive reactance with omega equal to 1000 radian per second. So knowing that omega is 10 to the power 3 radian per second, we can obtain the value of XL and XC. Now V1 and V2, which are represented in the problem as cos and the sine function, we have to bring it in the same individual function. So we can say that in the phasor format, V1 is 20 angle 0, whereas V2 is 20 angle minus of 90 degree to take into account the same sign convention. So same trigonometric rules we have to apply whether it is sine or whether it is cos. Now we can apply the Kirchhoff's current law, that is the nodal analysis, with algebraic sum of all the current at a particular node is equal to 0. So here all the current we can take entering the node and all the current leaving the node to be adding up together to form it as 0. Now we can write the KCL equation at node X. So we can convert these into its equivalent capacitive reactance and inductive reactance, and then we can write the equation of current is equal to V by Z form. So we can write the current as V by Z form, and appropriate sign convention we can take. We can take the current entering the node to be negative and current leaving the node to be positive, and these depend upon the user how to take the sign convention. Usually it is a good habit if we take all the sign to be outward so that all positive signs come, and the current will always flow from higher potential to lower potential. Then we will be having Vx minus V1 divided by the reactance of the inductor, Vx minus V2 divided by the reactance of the inductor here, the capacitors, and here we will be having the voltage divided by the resistance. So all the current will be adding up in accordance with Ohm's law and the KCL. Now we have only one variable, that is Vx. Now one variable in one equation, we can solve it to get the potential Vx, which comes to be 70.71 with angle of minus 45 degree. Now we can convert that in time domain instantaneous form, where the maximum magnitude is 70.71 and the source is in the form of a cos. So we have taken the result in the form of a cos. Frequency is 1000 and angle we are getting minus 45 degree. So this is the potential Vx which we have solved using nodal analysis. Next problem, we have to determine the current which is flowing through resistor R2. So this is the current which is flowing through 2 ohms and the source current which is unknown to us. Now it is given in the problem that both the sources, we have a voltage source and a current source, both are operating at omega is equal to 2 radian per second. If the frequency is not constant, it would not be possible to solve the problem. But since the frequency is constant, we can solve the problem by the circuit theorem. It is given that the capacitive current IC is equal to 2 angle 28 degree. So we have to obtain the value of IR2 and the source current IS. Let us see how to solve this problem. First, we can obtain the voltage across the capacitor. The reason is we have been given the current IC. So current IC is given and the capacitor we have to convert that in capacitive reactance, which will be equal to 1 by j omega c. So omega we can obtain from the source voltage. Now once we have got the value of the capacitor voltage, we can see that the resistor and the capacitor both are in parallel, so the voltage here will be the same. So I can determine the current which is flowing through the resistor IR2 is equal to capacitor voltage divided by the resistance. So get the current which is flowing through the resistor. Now we can apply the Kirchhoff's current law KCL here at this particular node. So the current IS is equal to IR2 plus IC. Now see, all these are having magnitude as well as in direction. So we have to solve that taking appropriate sign convention, otherwise there will be a mistake. So we have 1.5 angle minus 62 as the source current which we have computed. Now this source current can be written in the time domain form with 1.5 as the maximum magnitude. We have a cosine function, omega is equal to 2 and the angle is minus 62 degree. So this problem is solved using the principle of KCL and Ohm's law, basic Ohm's law. So this type of problem usually appear in MCQ type of questions. We have to determine the potential V1. So let us see how to determine the potential V1. Potential V1 is across the inductor of half Henry. We have a capacitor half farad and there is a dependent current source whose magnitude is 2V1. We have an inductor of 1 Henry and there are two sources that are independent current source. So here we have sine 2t and here we have 4 of cos 2t. So we have cosine function and the sine function, and we also have dependent current source. So let us see how to solve this problem using circuit theorem, either mesh analysis or nodal analysis. We have to convert the circuit in the appropriate format first. So the source 4 cos 2t can be written in the form of the phasor as 4 angle 0, whereas sin 2t can be written in the form of 1 of angle minus 90 because we are giving preference to cosine function. So we have taken here 0 degree and here minus 90 degree because sine function is there. Next, we will be converting the inductor capacitors into its equivalent inductive reactance and capacitive reactance. Once we have done that, we can obtain the theorems. So here we have two node problem. So there is a node 1 and node 2, and this is a common node which is at ground potential. Now we can write the Kirchhoff's current law equation at node 1 and Kirchhoff's current law equation at node 2, that is algebraic sum of all the current which is meeting at node 1 to be equal to 0. Similarly here all the current which is meeting at node 2 is equal to 0. So we see that the variables that we have is basically V1 and V2, which are the node voltages. These voltage V1 and V2 we have to find with these two equations. So we have two equations in two variables. Once we have solved it and we need to find what is the potential V1. So V1 in phasor format we are getting 1 angle minus 36.87, which we can represent in the time domain form as maximum magnitude is 1 cos of omega, that is 2t, minus of 36.86. So here we can represent either minus of 36.86 or plus 143.13. Both are having the same answer. We can represent this in the 180 degree format. Next we will go for Thevenin's theorem and Norton's theorem. So here we have to find the Thevenin's equivalent with respect to the terminal AB. So here we have terminal A and terminal B, and the source is 10 angle 0, and all the resistance, capacitance, inductance are already given in ohms. We have a dependent current source of 5I, where I is the current which is flowing from the source. Now we need to determine the Thevenin's impedance Z Thevenin, and we need to determine the voltage Thevenin. Then we can get one circuit which is equal to the source voltage. Z Thevenin will be in series, so we will be having Z Thevenin, and the source voltage is equal to Thevenin's voltage. So we will be having this terminal AB. Now the Thevenin's voltage is basically the open circuit voltage at terminal AB, whereas the Z Thevenin is the equivalent impedance when seen through the terminal AB. So we have to determine the voltage Thevenin and impedance Thevenin. So let us see how to do that. First, let us determine the value of voltage Thevenin, which is equal to the open circuit voltage at the terminal AB. So if we need to determine what is the voltage here at the terminal AB, I need to determine what is the current which is flowing through the source. Now this current will not flow this side because it is an open circuit. So the current will be flowing in this particular loop. So we can determine what is the current flowing is equal to the voltage divided by the net impedance of the loop. Once we have found the current, we can determine the Thevenin's voltage here at terminal AB with the voltage drop across the inductor and the capacitor combination. So if we know the voltage drop across the inductor and the voltage drop across the capacitor, we can apply the KVL concept here to determine the Thevenin's voltage, which comes to be 3.48 angle 84.3. Now once we have obtained the Thevenin's voltage, we can determine the Z Thevenin using voltage Thevenin by Norton current concept, where Norton current is basically the short circuit current at the terminal AB. So if we short the terminal AB, we will be getting a new circuit. Now why we are going by this method is basically we have a dependent source. If we do not have a dependent source, we could have easily determined the Z equivalent using series parallel concept. But that is not possible because of this dependent current source. So Z Thevenin is equal to voltage Thevenin by Norton current, and Norton current is the short circuit current at the terminal AB. So we have a two mesh problem here, mesh number 1 and mesh number 2. So we can write the KVL or the mesh equation in node number 1 and node number 2. So here we will be having the algebraic sum of all the voltages is equal to 0. So in this particular loop 1 and 2, we are going to write the equation. So we will be having the unknowns as the current which is flowing here and the Norton current IN for the KVL equation. So we can solve that and determine the Norton current, and this Norton current we can substitute here where the voltage Thevenin has already been found out. So we can find the value of Z Thevenin. So we can obtain the equivalent circuit of the Thevenin. Next problem, we have to determine the potential V0 across the 2 ohm resistor using the Thevenin's theorem, where we have the source 12 cos t and the capacitor 1 by 4 farad, 1 by 4 farad, and there is an inductor 2 Henry. We have a dependent current source of 3 I0, where I0 is the current which is flowing through 4 ohm resistor. So we have to solve this problem using Thevenin's theorem. So first, we have to determine the open circuit voltage. So we can open circuit the terminal across the 2 ohm resistor, because there we have to find the potential. So wherever we need to determine the potential, that will be my terminal. So here I have to open this 2 ohm resistor first to determine the Thevenin's voltage. Now when we open this 2 ohm resistor, I assume that the current I0 is equal to I1, which is flowing. Then I can write the KVL equation in the two mesh that we have. So here we have the mesh 1 and here we have mesh 2. I can convert these current source and impedance in parallel into the equivalent voltage source and impedance in series. So we can have a voltage source and one impedance in series that we can obtain using source transformation. So source transformation we have studied, and today also we are going to see in detail. So we can write the KVL equation for the two mesh 1 and 2, and then we can obtain the current I2. So here my variables will be I1 and I2, which will give me the current I2. So the Thevenin's voltage or the open circuit voltage across the 2 ohm resistor will be same which is across the 1 by 4 farad capacitor, because both are in parallel. So I can get the Thevenin's voltage, which is the voltage across the capacitor, is equal to 4.8 angle minus 36.87. Now I have determined the Thevenin's voltage. Next task would be to determine the Z Thevenin. When I need to determine the Z Thevenin, I can go from the concept of the Norton current, because here we have a dependent source. So we have to sort the terminal here, the 2 ohm resistor. We have to short circuit this one, and we can convert this source transformation of 2 Henry inductor in parallel with the current source as a voltage source in series with a inductor. Now we can apply the KVL concept and we can determine the Norton current which is flowing through this short circuit terminal. What is the current which is flowing here? So we can determine that using the KVL concept as 1.34 angle 63.43. Once we have got the Norton current, we can apply the Z Thevenin is equal to voltage Thevenin by Norton current. So we have got the Z Thevenin. So the circuit is like this. So we have voltage Thevenin in series with Z Thevenin, and now I can connect the unknown resistor which was removed from the network, that is the load resistor. I need to determine what is the potential across it, which I can determine using the voltage division rule. So the source voltage multiplied with the resistor across which we need to determine the voltage divided by the total equivalent impedance. So I'll get the voltage 1.27 angle 32 degree. Now here we need to determine the voltage V0 across the 1 ohm resistor using the concept of Thevenin's or Norton. We have source of 4 angle 0, that is a current source, independent current source. We have independent voltage source of 12 angle 0. We have inductor, that is J of 1 ohm, and we have a capacitor of minus or J 1 ohms. Others are resistors. We have a dependent current source of 2 Ix. So we have to determine the potential V0 across the 1 ohm resistor using the Thevenin's or Norton concept. Now we can see that a voltage source is coming between two meshes. So there we will be applying the concept of super node problem. So here we have to determine the unknown nodal voltage, that is V1, V2 and V3. We can take one common node, that is equal to 0 volt here. I need to determine the potential across 1 ohm resistor, so that will be my terminal. So the terminal will be A and B, which I need to sort it to find the short circuit current or the Norton current. Now we can apply the nodal analysis here. We can apply the nodal and super nodal analysis because we have a voltage source between the two nodes. So applying this nodal and super nodal analysis, we have to write the equations which are involving the node 1, 2 and 3. So on writing these equations, we have to solve the unknown variables, that is V1, V2 and V3, and apart from that we have one other unknown, that is Ix triple dash, which is the current flowing through 1 ohm resistor. That also we need to find out. So we have in total 1, 2, 3 and 4 equations in 4 variables. Once we put that in matrix format, we can get the unknown variables. Once we have got the unknown variables, we can apply the concept of Kirchhoff's current law at the node to get the short circuit current. So short circuit current is basically the Norton current which is flowing at the terminal AB. Now my circuit is, we have a short circuit current, that is the Norton current, and it is in parallel with the Thevenin resistance, or otherwise we can write this one as Z Norton. So these I have to calculate separately. So I will be having the Z Thevenin which is in parallel with the Norton current, and then I can connect the resistor which was removed from the network. Now the current we can determine I0, which is flowing through 1 ohm resistor using the current division rule, and then we can determine the potential V0, that is the drop across the 1 ohm resistor. So 1 I0 multiplied with 1, where I0 can be determined from the current division rule. So we will be getting the potential as 4 angle 143.13. Next topic, we are going to take the source transformation. Here we have to calculate the potential Vx across the 10 ohm resistor using the method of source transformation. We have a source 20 angle minus 90 and we have a capacitor minus J13 ohms and inductor is J4 ohms. So already these are in ohms, so we need not to worry and we can directly go for source transformation. So in the source transformation problem, we can see that the voltage source and a resistor are in series, which can be converted to a current source in parallel with the resistor. The current source, we can get it as the voltage divided by the resistance. So we will be getting the current as minus of J4, which is flowing in the network. Now we can say that the 5 ohm resistor and the combination of 3 plus J4 in the network, these two impedances are in parallel. So I can obtain the equivalent impedance Z1 for this parallel combination of the two impedances. After that, we are getting a new circuit where we have the parallel combination of these two as Z1 and there is a current source which I can get the equivalent voltage source in series with the impedance. So the voltage is equal to Is into Z1. So I will be getting a voltage source and then I can convert that into its equivalent impedances Z1. From earlier, we are having some resistance and one capacitor. I need to determine the potential across the 10 ohm resistor, which I can obtain from the voltage division problem. So voltage division we can apply in the series circuit and then we can get the answer to this problem, which is equal to 5.519 angle minus of 28 volt. So here this problem was much simpler using the concept of source transformation. If we would have solved this problem using mesh and nodal, the time would have taken little bit more. We go for maximum power transfer theorem. So the problem is choose a load resistance RL so that maximum power is transferred to it and calculate the actual maximum power that is being transferred to the network. Now here in the circuit we have a resistor of 1 kilo ohm, resistor of 5 kilo ohms, we have a resistor 17 kilo ohms and 300 kilo ohms. So only resistors are there. There are no inductors and capacitors. But the source is basically a function of time t, which is 2.5 sine of 440t millivolt. And here the voltage is V pi, which is there across 5 kilo ohm resistor. So let us see if we apply the maximum power transfer theorem, how to get this problem. So here knowingly I have not included any inductors and capacitors, but I want to make you difference what happened when the inductor and capacitor come in the next problem. So here you know that the maximum power transfer theorem says that the load resistor will be equal to the Thevenin resistance, then only maximum power can be transferred. So this is only when the circuit is having resistors, not the inductors or the capacitors. So we have to find the R Thevenin across the RL resistor when all the independent sources are disconnected from the network. I am getting the Thevenin resistance as 1 kilo ohm because there will be no current flowing here in this network because all things are opened. So we are getting 1 kilo ohm as the Thevenin resistance. Now once we get the Thevenin resistance, we have to get what is the Thevenin's voltage, which is basically the open circuit voltage at terminal AB. So we can apply the Thevenin's theorem here, which we have studied just now, to understand what is the Thevenin's voltage. So the Thevenin's voltage that we are getting is basically minus of 69.6 sine of 440t millivolt. So this is the Thevenin's voltage we are getting at the terminal AB, which is the open circuit voltage. Now the maximum power that can be transferred from the source to the load resistor is basically voltage Thevenin square divided by 4 times resistance Thevenin, under the condition that the load resistor is equal to Thevenin resistance. Then only maximum power can be transferred, which we are getting 1.211 sine square 440t microwatt. Okay, so this is the maximum power that can be transferred. Now in this problem we do not have any inductors or capacitors, so we have used this concept that the load resistor is equal to Thevenin resistance. Now in the next problem, we have a loudspeaker which is connected across the terminal AB, and what should be the impedance to obtain the maximum power dissipation. So we have two circuit A and B. We have to find the impedance to obtain the maximum power transfer theorem at the terminal AB. So we have two circuit. Let us see how to solve this problem. So circuit number A, we have to obtain the Thevenin resistance at the terminal AB. So here we need to determine the Thevenin resistance. Now only independent source is there. So it means if we have independent source and that is a voltage source, I can disconnect this source with a short circuit. So I will be sorting the voltage source and then I will be determining the equivalent impedance seeing at the terminal AB. So we can apply the series parallel concept to determine the equivalent Thevenin impedance. Now the condition for maximum power transfer for a circuit which is having both inductors and capacitors, or the AC circuit, is the load impedance has to be the conjugate of the Thevenin impedance. This is the condition to apply when we need to determine the maximum power. In the previous problem we have seen that the load resistor is equal to Thevenin resistance to get the maximum power transfer. Whereas when we have inductors or capacitors in the network, we will be having the Z load is equal to the conjugate. So here we have the conjugate of the Thevenin impedance. So we have the Thevenin impedance as 7.5 minus J 2.5. So since we have the conjugate, we will be having this negative sign as the positive sign for getting the load resistor problem, load impedance problem. Next circuit, we have to determine what is the Z equivalent here, and we have a current source and a voltage source. Both are independent sources, so we can replace that with open circuit the current source and short circuit the voltage source, and then we determine the Z equivalent for the network, which be equal to the Thevenin impedance. So the Thevenin impedance is coming to be 5.316 J 3.07 ohms. Now for the maximum power transfer, we will be having the load impedance is equal to the conjugate of the Thevenin impedance. So here we have a positive sign which will come to the negative sign in the conjugate. So we should put this impedance at the load terminal to get the maximum power transfer. Now in this problem, apart from determining the value of ZL, we will be determining the maximum power that is being transferred from the source to the load to get the maximum power. Now we have inductor and capacitor. So the source is 5 angle 0, which is independent voltage source. So first we have to determine what is the Thevenin voltage at the terminal AB by opening the load resistor ZL. So you open circuit the load resistor ZL and determine what is the Thevenin voltage. So we have got the Thevenin voltage as 2.236 angle minus 26.56 using the concept of voltage division we can apply. Next we can determine the Thevenin impedance Z Thevenin. So here what is the equivalent impedance after the voltage source is short circuited. Then we will be getting 1.8 minus J 2.4 ohms as the Thevenin impedance. The condition is the load impedance would be equal to the conjugate of the Thevenin impedance. So the negative sign will come to be the positive sign when we want to get the maximum power under this condition. And the maximum power we need to calculate. So first we'll calculate what is the current which is flowing in the network. So current which is flowing in the network can be calculated from the Thevenin's voltage. So we have the Thevenin's voltage and the condition of the resistor. So here we have the resistor is equal to 1.8. So this can be written as R plus J time X. So we have to choose only the resistor which is equal to 1.8. So that will give me what is the current which is flowing through the load impedance. So this is the current which is flowing through the load impedance. Now once we find the current, the formula is voltage Thevenin square by 4 times the load resistor RL. So when we are talking about RL, we have to take only 1.8 because that is the load resistor at the terminal AB. We are not dealing with the XL value when we are calculating the maximum power under the maximum power transfer theorem. So here we are putting only the magnitude, that is 2.236 square divided by 4 times the load resistor, which is coming from the concept ZL is equal to Z Thevenin conjugate. So these can be written as R plus JX. So the real part of that we are going to take as the load resistor. So this completes all the theorems under the frequency domain problem.